Hello everyone, today we'll talk about the problem count number of teams. In this problem we're given a list of unique integers, their order matters. In order to create a team of three values, of three soldiers, we have to choose a triple of indices, I, j, k, such that I is to the left of j, j is to the left of k, and the team is valid only if either the values are increasing or decreasing. So either rating of I is smaller than rating of j is smaller than rating of k, or the same thing but larger. And, well, the problem is called count number of teams. It's really count number of ways to create a team, because we're told that we have to count the number of teams, but every soldier can be part of multiple teams. So really it's just how many unique teams can be created starting from those n soldiers standing in the line. This problem we'll solve in n squared time, and we'll use a technique for which this is a very nice showcase, which is very common in situations like this, and probably one of the most standard problems that's very similar to this one, that showcases this technique, is to, in an array, count the number of subarrays, so subsequences, not necessarily contiguous, that are increasing and of length 3. This is a very standard problem, and the insight that we get from that problem is that in order to count a triple of increasing elements, we can look at the middle element, and now all the triples, so in essence, if we have here an array and we look at this middle element here, then for this middle element, all the triples in which it is a middle element is for every possible smaller element than it here, we can take either one of those. For every possible larger element than it here to the right, we can take either one of those. And all the triples for which this is the middle element are exactly the triples that take one s from the left, one l from the right. So the Cartesian product of those. So if we know the number of smaller elements to the left and larger elements to the right, then we can calculate the number of triples for which m is the middle element. We can iterate through all the m's and sum them up. This is our solution. And of course in our problem we have to count both smaller on the left and larger on the left, larger on the right, smaller on the right. In fact, we still need to only calculate one of those because the other one can be just calculated because all the values are unique. So every number to the left is either smaller or larger. Likewise for the right. So this is exactly what we'll do. We'll be counting all the triples and returning them at the end, and iterating for every middle element in our array. We'll count the number of smaller elements to the left, so up to middle. If it's smaller we add 1. Same thing with bigger elements to the right. And now our result will be increased by the number of smaller elements to the left times the number of larger elements to the right, because that is the size of their Cartesian product. That is the number of ways we can choose something from the left and something from the right to complete the triple. And of course the same thing would be for those bigger on the left, smaller on the right, which can be just calculated because we know that all the values are unique. So the number of elements bigger on the left is just the number of elements up to middle minus the number of smaller elements. Similarly for elements on the right that are smaller than our middle element. So this n squared solution, and it passes in this problem. There are of course ways to make it simpler, make it faster, well not simpler, make it faster, to probably make it run in n log n. I wouldn't be surprised if there is a way to do it using some sort of merge sort approach, like counting inversions, but I'm not familiar with it that much, so I can't tell you if it's actually possible. However, it's pretty obvious that those calculations for smaller elements to the left and to the right, that they probably can be made faster, and they can be made faster using either a binary search tree, because on a binary search tree we'll have essentially a sorted array in which we can find, using a binary search, the position of some element, and we can modify that array. So when we look at the binary search tree like that, then it's pretty clear, for instance, that we can find for all the elements to the, maybe for all the positions of elements smaller than our current element, so we'll be looking at middle soldiers starting from their smallest possible values and going up in sorted order then we can, for instance, maintain a tree of all the positions of all the soldiers that we've seen, and we can find where our soldier would be, the position of our soldier would be in that situation, and of course all the soldiers then to the left of him, we know that they are smaller because they are already in the tree, so we know their number if we know at which position in the tree our soldier would fit. So that is one way to do it with a binary search tree that allows us to say at which position we are, so how many things are smaller than us in that search tree. And also this kind of thing can be solved using a Fedwick tree, binary index tree, or a segment tree, something that allows us to modify positions and query ranges. And it can probably be used in even a similar fashion, where we'll just mark on every position that a smaller element appears, we'll mark it that it appeared, and then when we see, for instance, the 5th smallest soldier, we think about it as being the middle soldier, we can query everything before its position and count the number of ones that we have on that range. And those ones represent smaller soldiers, soldiers that we've considered as middle soldiers before, more specifically their positions, so we get the number of their positions. Maybe it's also possible to do it in a different way. But those are just another thing, a data structure difficulty on top of this problem. But I think that this observation about when we have 3 things, look at the middle one, when we have 5 things, look at the middle one, is very useful, and that problem in that case should just be used to showcase that particular pattern.